Okay, so let's just write down the Kalan-Samanzik equation in the form that it's usually written. So we have a d by dm. We have plus delta gp delta m d by dgp gp. And then we have a minus n delta eta delta m. And this is acting on Gn normalized equal to 0. And I got this just by equating the blue and red terms in the above box. Now we're going to manipulate this just ever so slightly. So we're going to multiply by m. So we've got an m d by dm. Then we're going to introduce some notation. So we're going to call beta to be m d gp dm. And then the second term becomes plus beta d by dgp. And then we're going to call gamma to be minus m delta eta delta m. And then this term is going to be plus n gamma on g n r is equal to 0. Good. So that's the Kalan-Samanzik equation as it's usually written. And there's a few things that I want you to pay attention to. So from this equation, the way that I've defined the beta function, I want you to pay attention to the sign. So beta was equal to plus m dgp dm. And this is going to be related to the puzzle that I was asked about. And then for the anomalous dimension, I want to just express things again in terms of the log of z. And this is nothing but m over 2 delta log z delta m. And now I want to stress something that I said before, but it's well worth stressing. The anomalous dimension comes from the wave function. From the wave function renormalization. Okay, good. So what we're going to do now, next, I want to tell you what is the solution to the Kalan-Samanzik equation. Okay? We're not going to write it down in general. We're going to write it down for the two-point function. And the first thing that I'm going to do is give you a little exercise. So we've already worked out the dimensions of the scalar field. And we said this was length to the minus 1. So you know that the dimension of the vacuum is just 1 because the vacuum is normalized to 1. So you could easily work out that the dimensions of the two-point function in position space is length to the minus 2. So I want you now to work out the dimensions of the two-point function in momentum space. I'll put a G2 there in momentum space, and you should find that this is length to the minus 2. So you just need to take into account the dimensions that are being introduced as a consequence of the Fourier transform. So the first equation that I'm going to write down is just purely bidimensional analysis. I know that G2 of P will be equal to. So momentum is inverse length. So I'm going to put in a 1 over P squared. Now I've already got the dimensions of the two-point function correctly. And then again, just by dimensional analysis, all that this can be multiplied by is a dimensionless function. So I'm going to multiply it by a function of P over M and the physical coupling. So this is what the solution to the Cullen-Samanzik equation has to look like. And I haven't done anything fancy. I've just used dimensional analysis. Now I'd like to rewrite the Cullen-Samanzik equation so that instead of taking derivatives with respect to M, I'm taking derivatives with respect to P. So M d by dm acting on G2 of P, I claim that this is equal to minus P d by dp minus 2 acting on G2 of P. Now, this is not a difficult equation to derive from what you've got here. You just take the green box, you know how things depend on M, so you can easily just go ahead and calculate the d by dm derivative. I'm going to suggest to you another way to think about this that I hope will be helpful. So my key observation is the following. If I take x d by dx, okay, so why am I looking at x d by dx? Well, it's because I've got an m d by dm and a p d by dp. So these are the kinds of operators that I'm studying. But if I take x d by dx and I apply it to x to the n, what I get is just n times by x to the n. So what does this operator do when it's applied to something? It's just counting the number of x's. And in exactly the same way, m d by dm will count the number of m's, and p d by dp will count the number of p's. Now take a look at the form of G2 of p. There are, for every m, there is an inverse p, or equivalently for every p, there is an inverse m. That's why the m d by dm went into a minus p d by dp. And then the reason why we've also got a minus 2 is that we've also got a 1 over p squared, which is not paired with any m. So we just need an extra minus 2 to appear there. So if that made sense, great. If it didn't, go ahead and do it by the usual rules of calculus, and then maybe come back to this argument and see if you can see it. So what I'm claiming is the equation that I've written in black under the green box just tells me the number of p's is minus, the number of m's is minus the number of p's minus 2. That's all that equation is saying, but you can also get it by calculus. So if we just write down what does the Cullen-Samanzik equation become, it becomes p d by dp. Here is the plus 2. Then we've got a minus beta. We've got a d by dgp. And we've got a minus 2 gamma. And this is acting on G2 is equal to 0. And this is the equation whose solution I'm going to write down. So the solution to that equation takes the following form. So G2, let's give its full dependence. It depends on P, it depends on M, it depends on the physical coupling. This is equal to 1 over m squared. No big shock. That is just getting the dimensions right. Then we've got a dimensionless function, curly g of g bar, and we've got an exponential. Exponential minus, we've got an integral from p primed is equal to m up to p primed is equal to p. And then we've got a d log p primed over m. And we've got a 2 into 1 minus gamma. Okay, so this is an equation worth thinking about a little bit. There's a few interesting things about it. What is this g of p? Well, this function determined here. So this would be determined by your Feynman diagrams. Determined by summing Feynman diagrams. So that's where your actual perturbative expansion for your 2-point function sits. Okay? And the Cullen-Samanzik equation doesn't determine that at all. What the Cullen-Samanzik equation does tell you is that the G bar, d log P over M, is equal to the beta function, and G bar at P is equal to M is equal to your physical coupling. So I've given you a differential equation, first order differential equation to solve, and I've told you its initial condition. So one initial condition is needed to specify the solution. And then what you can see is this curly G of G bar will be the usual perturbative expansion just by summing Feynman diagrams. So we're getting that usual expansions appearing, but with this G bar. And G bar you can interpret as your running coupling, the coupling at whatever scale you're looking at. The second exponential factor, well, you can see that if you act with a P d by dp, it's only going to hit the upper limit, okay? And the P is going to get swallowed up by the d log P, which gives you a 1 over P. And then you've got a 2 minus 2 gamma. So it's going to cancel out. So this exponential factor sitting over here cancels out those two terms once you act with P d by dp on it. And after you act with the P d by dp on the G bar, that'll cancel out the minus beta d by dgp term. Okay, so this is the solution to the Cullen-Samanzik equation. So we'll continue in a minute.